Hi everyone, I'm Anca Nitulescu, and today I will talk about SnarkPack, Practical Snark Aggregation, which is a joint work with Nicolas Gailly from Protocol Labs and Mary Maller from Ethereum Foundation. So, in brief, what we are doing, we are taking a lot of snarks and we aggregate them together into a very compact proofs that will be the final aggregated proof. So what snarks are? As their name says, they are succinct non-interactive arguments of knowledge, so they are proof systems that allow for a prover to demonstrate to a verifier that some NP statement is true. And this is done in a way that has the following properties. It's succinct, so the proof size should be independent on the NP witness size. It's non-interactive, so the prover and the verifier don't have to exchange rounds of interaction in order to verify the proof. It's an argument in the cryptographic sense, like the soundness holds only against computationally bounded adversarial provers. And it's more than sound, it's knowledge sound in the sense that a witness can be efficiently extracted from a prover that can convince a verifier. And it can be zero knowledge in the sense that the proof should also conceal all information that is not related to the correctness of the statement. So the verifier doesn't learn more than necessary. So why we are using snarks? A good application for it, it's proof of storage, where, for example, Filecoin, where we have these two actors, storage providers, which onboard storage capacity to some decentralized network, and they earn block rewards in exchange. And because of this, they become provers in the system. They need to prove this storage is there for the network. And another part of the network is verifiers. They ensure the data is being stored. They check that the provers are maintaining and secured the data to the network. So in order to build such a system, we just use snarks as proofs for the storage. In order to prove each 32 gigabytes of units of storage, we will call this sector. We have to onboard 10 snarks, 10 proofs in a public ledger in order to show the persistence of this storage. So because the system cannot scale well, we have too many proofs per day for a network that grows fastly. We want to make this 10 snarks per unit of storage somehow lighter. So one idea is like the system needs to verify many snarks in the same time, and we can do it by batching the verification process. This doesn't improve the proof size. The verifiers still need to look at all the proofs and kind of combine them together in order to batch them in the verification process and to gain something in the verification time. So we want to improve this by adding aggregation, which will differ from batching in the sense that the proof size will be shorter. The verifiers have to look only at something small, and the verification time will also be improved as much as in batching, but considering just the final step where the proofs are already combined together. So how does it work? Let's first see the background we need for this. Like I will talk here only about the Snark system GROD16, which is the state of the art today. This is the smallest size proved Snark that exists in the literature, and it's built on top of bilinear groups. So quickly reminder of what bilinear groups are. We have these cyclic groups. This is a multiplicative notation. We have G1 generated by aggregation in the exponent. When we have an element G to the A in the first group and H to the B in the second group, we can check that with this pairing that another element in the target group corresponds to AB in the exponent. Okay. So how does GROD16 proof work? We have this setup phase where we have to generate a structure reference string, which consists in many group elements that have some secret in the exponent, and the secret is supposed not to be known by anybody. It's a trusted setup. And then based on this trusted setup, the prover can generate a short proof that consists in 3 group elements: A in the first group, B in the second group, and C in the third group. And in order to verify, the verifier should just apply this bilinear map, the pairing, to the elements of the proof and to some other element D that is generated from the input to the proof, from the statement to this proof, and some keys from the public structure reference string. Great, so this is all we need to know to understand our constructions. So what we are doing, as I said, we start with many snarks. They have all this form. We have 3 group elements in each proof, and we have to verify a pairing equation for each of them. What we were doing in a batch verification, we were taking many verification equations, and instead of doing them one by one, we were combining them in a way such that the final check, the pairing check at the end, would be shorter than doing each one of them independently. So the idea is quite simple. If we want to sample randomness R in order to combine this pairing equation, we will just make a random linear combination of them with the powers of this randomness R, and obtain in the end, by the homomorphic properties of the pairing, by linearity, as I said, a batch verification equation, which consists in only one pairing equation at the end. And this batch verification, checking one linear random combination of all the verification equation, guarantees us that all the initial equation hold. Great. So the idea is very simple for the aggregation. We wanted to defer most of this combination of proof part to the prover. So the aggregation, the linear random combination of the pairing equations, will be done by the prover, and the verifier will have just to check one final pairing at the end. However, this will not work without some guarantees that the combination of the initial proof elements was done correctly. So what we are left to do is the prover to convince the verifier that they indeed recombine the proofs with a linear random combination as expected, so that the final check will guarantee that the initial equations were holding with respect to the initial elements in each proof. So if we look closely to how this random linear combination of pairings looks like here, we will see that we can rewrite it as an element ZAB, which is the product of all the pairings with the first element of the proof AI and the second element BI to some randomness, this random power of the randomness. And ZC on the other side of the equation will be the product of the multi-exponentiation between all the third elements of the proof, Ci, to some powers of this random R. And D is, as I said, an element that the verifier should compute from the statement itself and some verification key. So we have to only check ZAB equals to a pairing of some element ZC, which is in the first group, and D, which is the second group. But all the prover needs to show us is that ZAB and ZC were correctly constructed, starting from the initial proofs AI, BI, and CI. So let's go to more detail about this construction of the proving of ZAB and ZC. So the tools we will use here come from a previous work, Proof of Inner Pairing Products and Applications from Boons et al. And this allows to show that some equations, some generalized inner pairing product equations, hold between group elements. So here in yellow, there are multi-exponentiation inner product proof for what we call a multi-exponentiation of a group element vector A with some exponents B that are in the field. So we have this product of AI to BIs. And the second one in red here, it's a generalization of inner product for target group elements for pairing products. So here we have elements in a vector from the first group A and a vector with elements from the second group B, and we check that this product of pairings between AI and BI it's indeed equal to the result, the claim result that is in a target group, this inner pairing AB here. And this is done with respect to the committed vectors A and B in some commitment schemes that is compatible with techniques to prove the equations in the left. Okay, so what we can remark here is that, remember that we needed to convince the verifier that ZC that was computing started with some elements C in the first group, and ZAB that was computing using pairings with elements that are in the first group in the second group are consistent with what the initial proofs were containing. So if we look at ZC and ZAB, we can write them as a multi-exponentiation inner product and as a inner pairing product for the ZAB here, with respect to the vector A and B to the R, which is a vector in the second group with the randomness R. Great. So this looks exactly what our prover needs to demonstrate to the verifier. We will only have to commit to the vector C and commit to the vector A and B, and then show that the values ZC and ZAB are the respective inner products that the verifier needs to check. Okay, the problem with this is that the commitment showed in prior works to demonstrate such MIPP and TIPP proofs are requiring a very special trusted setup to generate parameters that are structured in a way that this commitment can be used for further proofs. And in practice, trusted setup are something that we want to avoid because of this very complicated MPC ceremonies that should be executed in real world, where many parties should come together and show they were honestly playing in the MPC computation and then destroy their secret data and ensuring that this is a trusted one. So instead of rerunning such a ceremony, our idea was to aggregate snarks from existing CRS, a common reference string, more precisely structure reference string, so from settings that are already used for the snark, for example. So GROD16, as I said, needed a trusted setup itself, and those are mostly powers of taus and other elements, but powers of taus is what we call this secret powers of some random value in the exponent of the first group and of the second group in the bilinear group I was mentioning. So having this as a setup, we can run GROD16. And we were thinking of doing something that relies on the same kind of structure setup. And what we found is a commitment scheme that needs two copies of such a trusted setup that are compatible in the sense that they have the same generators for the two groups, but different randomness for the powers encoded in the exponent. So here the different randomness are alpha for the first trusted setup and beta for the second, and we have such trusted setup in the practice. One is from Filecoin system and one is from Zcash system. So using those powers of tau, part of the GROD16 trusted setup, we can run aggregation of GROD16. So first, we have to define new commitments that use this trusted setup as commitment keys. And how they work: to commit to an element C in the first group, we just do some inner pairing product between the elements in C, the vector C, and the vector of some public key, which is the trusted setup. Here we split the public key in V1, that is the second group with the first randomness alpha, and V2, which is in the second group with the second randomness beta. So the commitment is two group elements, as shown here, that are easily computed just using this inner pairing product. And in order to compute a commitment to an element, to a vector in the first group with a vector in the second group, we can pack them together in the same commitment. So we gain one target group element for the committing part, as is shown here, A and B. I commit in the same commitment with two elements. So now it's time to say how Snark aggregation works. We have many proofs that are all consistent in three group elements, A, B, and C. And we will commit to the vectors A, B in one commitment, as we said, to target group elements, and to vector C in the second commitment, which is to target group elements also. And once we have this, we can run the multi-exponentiation inner product proof for C and the randomness R that is generated by random oracle. And then we run the target inner product for pairings, where we have the vector A and the vector B exponentiated to the consecutive powers of the randomness R, and we show that these values satisfy the kind of equation that were required for the random linear combination, and send the final values of this inner products ZC and ZAB together with the proof that they were computed correctly. Great. So what the verification needs now? It takes this logarithmic size proof that shows that ZAB and ZC are correctly generated, and those are already multiple proofs packed together in a single element, ZAB for the left side of the checking equation, and for the pairing check in the right, we just have to pair ZC, which is a first group element, with D, which is an element derived from the all the statements together. Great. So we have an implementation for this, and the library is in Rust. We also combined the two libraries for the powers of tau, the setup we needed, and we use BLS 12 curves. This demonstrates that verifier time pays off starting at 2 to the 5 proofs to aggregate, compared to the batch verifications. And this is logarithmic, it's logarithmic increase in performance, so that's it's really better than the batching verification increasing. And the proof size, of course, is also logarithmic in the initial proofs to aggregate, with respect to batch size, where that just increases linearly. The proofs are not aggregating in any way in the batching solution. For the aggregation time, we have this 8.7 seconds for 8,000 proofs. So that means that 2 to the 17 proofs can be done in 2 minutes, which is not a lot of overhead for very powerful provers that will aggregate a lot of proofs in just 2 minutes. So the application is Filecoin at the beginning, and I want to just show how much this improved the system. So now, using these packing techniques, this aggregation of snarks, we can onboard 2,000 more times proofs on the chain. So we take these different 10 snarks for each sector and we aggregate them together, and what is onboarded on chain is just the aggregated small proofs, which is logarithmic in the number of initial proofs. And this allows for a lot more proofs to be aggregated in a shorter time. And the verification also, it's fast, so this is verified in 20 minutes, in 20 milliseconds for each 2,000 snarks, while before we had it to aggregate and do it one by one. Okay, so the conclusion of this work is that the main feature and the main difficulty was here the trusted setup. So we were thinking of future work where we have transparent snarks and how to aggregate them, so we get rid of any trusted setup. The optimizations that we can achieve here are better curves or better commitments or new inner pairing techniques for these proofs that we use. And also, this technique is quite general for any pairing-based primitives that only ask a verifier to check a pairing equation. So we were wondering if there are other applications that can be interested in the field. So this concludes my talk, and I'm happy to invite you to read our paper. This is publicly on ePrint, and the link is here. Thanks for your attention.